In last lecture, we have find the magnetic field on the axis of current carrying loop. So, the magnetic field on the axis Px is equal to mu0 bata 2 into n into I r square bata r square plus x square power 3 by 2. Here I is the current passing through it, m is the number of turns of the coil, r is the radius of the coil, x is the distance between the center of coil and the position on the x-axis. So we have find it. Now we can write this relation also in terms of magnetic moment. The magnetic moment of the coil will be equal to the total current multiplied by the area. Total current is Ni multiplied by area is pi r square. Area of cross section of the coil. So magnetic moment capital M will be equal to Ni into pi r square. So we substitute here. We multiply pi and divide by pi. So P is equal to mu0 bata 4 pi 2m r square plus x square ka power 3 by 2. So this relation is magnetic field on the axis in terms of magnetic moment. Now we will take the special case for the magnetic moment. Magnetic field on the axis of the circuit. Suppose we take the point which is at the center of the coil. It means the x is equal to 0. When we put x is equal to 0, then Vx will be equal to mu0 Ni r square plus x is 0. So r square r power 3 by 2, this will be r cube. So r square will cancel. So it will be equal to mu0 Ni r square divided by 2r cube. R square cancel, here will be r mu0 Ni bata r 2r. So this relation we have already find when we have find the magnetic moment at the center of the coil. Now so we can also write this relation in terms of magnetic moment. Then here we put second x is equal to 0. Then BC will be equal to mu0 bata 4 pi 2m bata r cube. Now case number second, when we have to find the magnetic at the point which is at a distance apart. So this is their coil and this distance is r by 2. So x is equal to r by 2. Then Vx on the axis at the distance r by 2 from the center of the coil will be equal to mu0 Ni r square divided by 2 r square and x is equal to r square by 4 power 3 by 2. We solve it, then it goes mu0 Ni bata 2 r into 5 bata 4 3 by 2. So this will be equal to 8 bata 5 root 5 into mu0 Ni bata 2r. mu0 Ni bata 2r is the magnetic moment at the center. So we can say if we divide 8 by 5 root 5, it will be equal to 0.716. So the magnetic field at a distance r by 2 will be equal to 0.716 into the magnetic field at the center of the coil. Now, how the magnetic field varies with that? Now we are going to change the x value. U is constant, M is constant, I is constant, radius of the coil is, and if we vary x, then D will change. So if we plot a graph between magnetic field on the y-axis and x on the x-axis, then we value the curve like this. at this is the center, here x is equal to 0. So here the magnetic field will be maximum. Here we have found it, and this will be a maximum value. So B maximum will be equal to mu 0 n I divided by 2r. This is the maximum value when x is equal to 0. So x is minimum, B is maximum. So here we say the maximum value of B maximum will be equal to mu 0 Ni bata 2r. And x increases, then B decreases, and the curve is like this. If we look at the curve here, then at this point is I, and before this the curve is concave, and after this it is a convex, and here is curve. So here at this point the curvature changes from convex to concave, and this point is known as the point of inflection. Now point of inflection will be a point where the curve changes its shape from convex to concave. Now we can find the value of, you can find the position of the point of inflection. Point of inflection, at the point of inflection, the dbx bata dx will be constant. So here db bata dx will be constant. So d2b bata d2bx bata dx square will be equal to 0. So if we take this value of bx, we differentiate twice with respect to x and put it equal to 0, then the value of x will come to be r by 2. At this point, when there is the r by 2, here is a point of inflection where the curvature changes convex to concave, and its position is r by 2 from here. So as b is x is 0, b is maximum. As we increase the x, b decreases, and as x tends to infinity, b tends to 0. So as we increase x, we change 0, and at the point x is equal to r by 2, then it will be the point of inflection where the change of magnetic field with dx is constant, or the second differentiation d square bx bata d square, that is equal to 0, and this point will be, if we calculate it, then we will get the value of x is r by 2. So at the r by 2 there will be a point of inflection, and at this r by 2 the value of magnetic field here will be equal to 0.716 into, so it will be less here, it will be 0.716 times the magnetic field at the center. Now if you want to find the magnetic field at a point, then magnetic field cannot be found by simple a coil, because the value of B changes as x changes. For a very small change in x, then B changes. So to measure the magnetic, we have to use the magnetic needle. So there is a definite size of the magnetic needle. So the value of, since B is not constant, so we cannot measure the magnetic field using single coil. So what we'll do, we will use a Helmholtz coils. Helmholtz coils have two coils. There are two identical coils. One coil is this, another coil is this. They are identical, and distance between these two is equal to the radius of the coil. So the radius of this coil and this coil is same. Number of turns is same. The current is same. The current is flowing in the same direction for the both. So, and the distance between center is this r. And if we take this here, the axis, then we will find the magnetic field, and we plot the magnetic field of first coil and second coil. This is the for the first coil, and this term is like this is for the second coil. The maxima for both are same. The minima will be equal to maximum will be equal to BC will be equal to mu 0. It will be equal to mu 0 and I bata 2r. So this will be the magnetic field equal for this. Now since the magnetic field due to single coil, first coil and second coil, they are in the same direction, and direction is the x direction. Direction will be in the back direction. So they will be added. So total magnetic field effect due to both the coils is given by this dotted curve. And this value is here, and this value is 1.432 into the magnetic field. In books, this figure is given wrong, and they have said the constant magnetic field here. It's wrong. The magnetic field is higher than BC, and it is 1.2. It is at nearly 1.5 times this. So it will be like this. So from here to here, we will see the magnetic field is constant. Due to both the magnetic field constant, so we can use for the measurement of magnetic field using Helmholtz coil, and it cannot be measured by the single coil. So this is all about the magnetic field due to the coils. Now we will find the magnetic field for the special cases. Suppose this is a wire and it is in the shape of the arc, and its length is L, and its substrate angle theta with the center. This is the radius of the circle. This is the arc. The radius of arc is R, and we have to find the magnetic field at this point, which is at its center. So we can find it using the Biot-Savart law. So if we take a small dl here, we take any small dl here, then dl is perpendicular to the arc. So theta is equal to 90. So the magnetic field due to this small dl will be dp will be equal to mu 0 bata 4 pi I dl sin 90, because angle between dl and this is 90 divided by r square. So sin 90 is equal to 1. So it will be equal to mu 0 bata 4 pi I dl bata r square. Now if theta is this angle, then angle is equal to arc bata radius. So theta will be equal, arc is L divided by radius. So L will be equal to R into theta. So the total magnetic field due to the entire arc D will be equal to integral dV. It will be equal to mu 0 bata 4 pi. They are constant. I is constant. R is constant. We take outside and integral dl. dl will be equal to the L, total length, and total length is equal to theta into R. R1 will be cancelled. So D will be equal to mu 0 bata 4 pi into I into theta bata R, and its direction will be by the thumb rule, right hand thumb rule, it will be in the inside the board. So the magnetic field at this point P will be equal to mu 0 bata 4 pi I into angle theta divided by R, and the direction is perpendicular to board inside it. Now if the theta is equal to 90, means it is like this. This angle is 90, R, and this is your current I is passing through it. Then what will be the magnetic field at this point P? The magnetic field at the point, just we put the value of theta here. So the B will be mu 0 beta 4 pi I into theta beta r. We substitute the value of theta. Theta will be equal to pi by 2. So we put the theta is equal to pi by 2. Then B will be equal to mu 0 beta 4 pi I beta r into pi by 2. So this will be equal to 8r. mu 0 I beta 8r, and we will find the value of this. So simply we substitute here theta is equal to pi by 2, then here it will be mu 0 beta 4 pi I into pi by 2 r. So it will be equal to mu 0 I, pi will cancel. So here pi will be cancelled. So this will be equal to mu 0 I beta 8r. So this will be the value of magnetic field. Now second exercise, we find the magnetic field if there is a wire and it is in shape of this. It's a straight wire, this is the center and this is the half circle or semicircle, and current I is passing through it. Or it is the reverse direction here, and same radius of this is also r, and current passing in the same direction. What will be the magnetic field at its center P here? Now we are having the three parts. One is AB, another is the curved part BC, D, and third is your DE part. So for AB and DE part, they are in the same direction with the center. So theta will be equal to 0, sin 0 is equal to 0. Therefore, the magnetic field due to the straight portion AB and DE will be equal to 0. Now, for this curved path, so magnetic field here will be equal to 0 AB, then this is equal to of BCD plus 0 for this one, and we will find the value of BCD, and this will be 0 I beta 4r. So this is just for complete circle. If it is a complete circle, then it was equal to mu 0 into I beta 2r. So it will be 50%. If the half circle is there, so it is mu 0 I beta 4r. And direction of magnetic field again given by the right hand thumb rule, and this will be in the perpendicular direction to the pole. Now, if the circuit is like this, what will be the difference? Only the difference will be there. The result will be same. Only the direction will change. Now here the current is going to this. So the magnetic field here will be upward, and here it will be upward and perpendicular to the board. And for this it is downward or inside the board perpendicular. So we will take next few examples on this subject. Next exercise number 2. We are having two coils whose radius is R1 and R2. The current is R1 and R2. Current is I1 and I2. Their center is common. And we have to find the magnetic field at the center. Now in the first coil it is clockwise, it is anti-clockwise, current is everywhere, and in the second coil it is also anti-clockwise. So magnetic field due to inner and outer, that will be by the right hand thumb rule, it will be outward. For this, so B1 and B2, they will be in the same direction. Now what will be the magnetic field at the center due to the inner coil? It will be equal to B1 is equal to mu 0 into current I1 into 2R1 and its direction is perpendicular to the board upward. Now for the second coil, the current is also in the anti-clockwise, so the magnetic field V2 will be equal to mu0 I2 divided by 2R2 and its direction is also perpendicular to the board upward. So the total magnetic field will be sum of these two because both are in the same direction. So the magnetic field B will be equal to B1 plus B2 will be equal to mu0 by 2. A common I1 bata R1 plus I2 bata R2. If I1 and I2 are same, then we put it I1 is equal to I2 into I. Then magnetic field will be equal to mu0 I bata 2 R1 plus R2 divided by, and its direction will be perpendicular to the board. Now we take the same case, similar case here. Only the difference is here the current in inner is anti-clockwise and outer coil is clockwise. So the direction of magnetic field by the right hand thumb rule for the inner it will be downward. It is upward, and for outward is inward. So the magnetic field at the center, which is the common for both the coil, whose radius is R1 and R2, current is I1 and I2. Here current is I1, here current is I2. I2 is in clockwise, where I1 is in the anti-clockwise. So the magnetic field due to the inner coil B1 will be equal to mu0 current I1 bata 2R1 and its direction is perpendicular to the board outward. For the outer coil, the magnetic field P2 will be equal to mu0 current I2 divided by 2R2 and its direction will be inside board. Since R1 is less than R2, therefore this V1 will be greater than V2. So total magnetic field will be equal, B will be equal to V1 minus V2. This will be equal to mu0 bata 2 I1 bata R1 minus I2 bata R2. If I1 and I2 are common or same, then we will and B will be equal to mu0 I bata 2 R2 minus R1 bata R1 R2 and its direction will be perpendicular to the board outward. So the results are same. Only difference here is the positive and is the negative. It is due to the current. In first case they were all in the anti-clockwise, and for the second case one is clockwise and others, so it is minus. Now we take the next example, example number 4. If this wire is there and it is in the shape, then this is the center and this is the inner circle, half semicircle, and this is the half semicircle. His radius is R1, his radius is R2. I1 is current flowing through this. So current I1 is passing through it. So the direction of current is this. Here it is the anti-clockwise and it is the clockwise. So the magnetic field will be in the opposite direction. For the here we take the inner circle, the inner semicircle BQC. Then magnetic field BQC. This will be equal to mu0 bata 2 I1 bata R1 and its direction is inward. For the second semicircle, the magnetic field will be equal to for BEA. This is anti-clockwise. This is clockwise. So it will be equal to mu0 bata 2 I2 bata R2. here I1 bata R1. So now here R1 is less than R2, so this factor will be more than this. So total magnetic field will be equal to the difference of these two. Now for the straight portion AB and CD, the magnetic field will be equal to 0 because they are in the same line. So theta is equal to 0. Therefore, the magnetic field due to AB straight portion and CD is 0. So total magnetic field will be equal to B1 minus B2 because B1 is greater than B2. So total magnetic field is equal to BQC minus BAPD. This will be equal to mu 0 current is same mu 0 I bata 2 1 bata R1 minus 1 bata 2. So B will be equal to mu 0 I bata 2 R2 minus R1 bata R2, and the direction will be inside the board perpendicular inside it. So in this way we can solve the problem and we can find the magnetic field due to the single coil, due to the double coil, or in this shape. So we have find the magnetic field in all the three cases.